Alright guys, welcome back. In this video we want to use Castigliano's theorem to find the deflection at the free end of this beam, and notice there's no point load there, but Castigliano's theorem basically depends on the fact that there's a point load acting at the point that we're looking for the deflection from. So in cases like this where we don't actually have a point load at the point that we're looking for, what we do is we introduce a dummy load with a magnitude of 0. So I'm just going to draw it on here, with dashes, and we're going to call this QA. And this will ultimately be equal to 0, but we're not going to substitute in the numerical value for it just yet. So we can write the expression using Castigliano's theorem, basically saying that the deflection at the point that we're interested in this case it's YA, is equal to the partial derivative of the total elastic strain energy of the beam with respect to QA. So you might see this in general terms where it's yj is equal to the partial derivative with respect to qj. We already know that we're looking for point A, so we might as well put in a meaningful subscript with that. Okay, and what we can do is we can expand this out a little bit. We know that the total elastic strain energy is equal to the integral of 0 to L of m squared over EI dx. So what we do here when we're taking the partial derivative of it is we separate out those two m's, and so we put the first one over EI, and then we write this multiplied by the partial derivative of the second one, so the partial derivative of the m, let's write that a little bit nicer, with respect to QA, and don't forget the dx there at the end. Okay, so for this to work, we need the expression for the internal moment in terms of x, and we can get that by drawing basically a free body diagram with a virtual cut here. So we know that we have QA pressing down right at the end. Halfway along we're going to have Wx, this is the resultant force from the distributed load. We're also going to have the applied moment Ma here, and for this to be Wx, that basically means that this distance has to be x, and it's acting at a distance of x over 2. Alright, we can also draw on the internal shear, that's V, and the internal moment as m. Alright, so we can take the sum of moments about some point. Let's do the sum of moments right here. That's going to be the easiest calculation for us. So we'll start off with, we have m plus, what do we have? We have ma. These are all going to be going in a counterclockwise sense around this point. So plus qa times x plus wx times x over 2. And this has to be equal to 0 for the sum of moments. What we do is we move everything over to the other side, so we get this expression where we have m is equal to, what do we have? We have negative qa x minus 1/2 wx squared minus ma. And this is actually our expression for m in terms of x, right? Because as x grows, this stuff's going to be changing and m is going to be changing. So this is our expression for m in terms of x. And what we also want is the partial derivative of this expression with respect to qa. So we write delta m with delta qa. And what we do is when we take the partial derivative, basically we set qa to the variable and everything else to constants. So when we go and take the derivative of this one term at a time, this qa gets reduced to 1, and so this first term becomes negative x. And there's no qa in this term, and there's no qa in this term, so these are just considered constants. And when you integrate, or when you derive a constant, those just drop off to 0. So now we have an expression for the partial derivative of m with respect to qa, and we also have an expression for m, and basically we can just plug those into the respective places right here. So what we want to do is we can bring out the 1 over EI to start with. Set this from 0 to L. And at this point, when we plug it back in, after we found the partial derivative, now we can set QA to 0. Notice if we had set QA to 0 here, then if we took the partial derivative of it, it wouldn't work. Taking the partial derivative of 0, that just doesn't mean anything useful to us. So what we want to do is we want to set this equal to 0 now when we plug it back in. So the whole first term here is going to go to 0. So we're left over with negative 1/2 wx squared minus ma. That is the expression m once we've set qa equal to 0. And then when we multiply in the partial derivative of m with respect to qa, that's just negative x. All right, and then just put dx on the end. So from here on out, it's pretty straightforward integration. We have 1 over EI. We can just distribute this x, this negative x in, so we have 0 to L. That negative is going to cancel out with this negative, so we are left with 1/2 Wx cubed plus MAX dx. All right, so let's do this integration now. So we get 1 over EI is going to be multiplied by, well, this will go to x to the power of 4 times a quarter, so we have 1/8 Wx4, and we're going from 0 to L, so we can just swap out this x here with an L, so WL4, just like that. All right, this guy here is going to go to 1/2 x squared, so this becomes 1/2 MAX squared, and again we can just substitute in the L right away. So we get 1/2 MAL squared. All right, so we have values for W, MA, L, and EI, so let's plug those in. And then if we do that final simplification, we're going to find that YA is equal to 0.0008 meters, and we can just convert that to be 0.8 millimeters. And you'll notice that is a positive value and it's going downwards. The reason this is positive is because it's going in the direction of QA that we defined to be going downwards. So there we go. That is how we use a dummy load to find deflection in a beam using Castigliano's theorem where there isn't actually an applied point load. And if you wanted to, you could compare this with using the method of superposition for finding the displacement at the free end of a cantilever beam like this. Basically do one system where we have this distributed load, do another system where we have the applied moment only, and then add up those two deflections, and you'll see that we get exactly the same answer.